In this video, we're going to be talking about conjugate acid-base pairs. We're going to introduce the idea of a conjugate acid-base pair using an example reaction. The example reaction is between hydrogen fluoride, or HF, and water. So hydrogen fluoride is a weak acid, and when you put it in water, it will dissociate partially. So some of the HF will dissociate, and you'll get fluoride minus ions. And then that dissociated H plus ion. So this dissociated H plus ion will get donated to our water. So water then becomes H3O plus, or hydronium. And so this process is in dynamic equilibrium because it can go forward and it can go backward, and eventually those two rates are equal and they're both happening at the same time. So in this reaction, we have a couple things going on, and we're going to think about it in terms of hydrogen ions being exchanged. So if we just look at the hydrofluoric acid and we look in the forward direction, our HF is becoming F minus, and it's doing that by donating or losing, so I'll put a minus for losing a proton. So our HF loses a proton. That forms our F minus, or fluoride ion. And then we can look at that same process happening in the backwards reaction. So if we look at the backwards reaction, which is also happening, the fluoride ion can pick up or accept a proton from somewhere. So it can pick up an H plus. So I'll have a plus, H plus here. And so when fluoride accepts a proton, we reform our HF. So we can see that HF and F minus have this special relationship where you can form one or the other by losing or gaining a proton. And we can see a similar relationship between water and hydronium. So water here, we said water is accepting a proton from HF. So we see that water will gain a proton, and that will give us hydronium. In the reverse reaction, hydronium can lose a proton to reform water. So minus H plus. So again, we have these two species, water and hydronium, that are related to each other by having or not having one H plus. So in chemistry, we call these species that are related in this way conjugate acid-base pairs. So the official definition, or my official definition of a conjugate acid-base pair, is when you have two species that are related to each other. Let's see, two species that are related to each other, related by one H plus. In this case, we have HF and F minus that are related to each other by that one H plus. And so HF and F minus are a conjugate acid-base pair. We also have water and hydronium, which are also related by that one H plus. So water and H3O plus are also a conjugate acid-base pair. You can probably tell from the name, but whenever you have a conjugate acid-base pair, one thing in the pair will be an acid, and the other thing will always be a base. The definition of which one is the acid and which one is the base comes from the Brønsted-Lowry definition of acids and bases. So the Brønsted-Lowry definition says anything that can donate an H plus, so anything that will give away an H plus, is an acid. So we can see that in this case, our hydrofluoric acid is acting as the acid in the conjugate acid-base pair. And that means that fluoride has to be acting as the base. And that makes sense because the Brønsted-Lowry definition of a base is something that will accept an H plus. And that's exactly what it does in the reverse reaction. Your F minus will pick up an H plus and go back to your acid. So we can also look at water and H3O plus. So here, water is gaining a proton or accepting it. So water is acting as a base. And in the reverse reaction, H3O plus is donating a proton, so H3O plus is acting as an acid. the relationship between conjugate acid-base pairs, we can write a little bit more generally. So if we represent any generic acid as HA, so this is our acid, we said that a acid is something that donates a proton. So it'll lose the proton, and when it does that, it will form the conjugate base, which is represented by A-. In the reverse reaction, our base, A-, can gain a proton and remake our acid, or conjugate acid. So whenever you have two species that have basically the same formula, which we abbreviated here as A-, except for one has an H+ and one doesn't, then you know you have a conjugate acid-base pair. So let's look at some more examples of conjugate acid-base pairs. We saw above HF, or hydrofluoric acid, its conjugate base is F-. So here, HF is our acid, and when it loses that proton, we are left with F-. We saw in the same reaction that water can act as a base. So if water is our A-, if that water accepts a proton, it forms the conjugate acid H3O+. So the example we've gone through so far, HF, is for a weak acid, but we can also talk about the conjugate base of a strong acid, like hydrochloric acid. HCl is a strong acid, so that means it completely dissociates. So it gives away all of its protons, and when it does that, we're left with the conjugate base, chloride. So even though chloride isn't particularly basic, it's still the conjugate base of HCl. And last but not least, we're going to go through two examples where it looks like we might have a conjugate acid-base pair, but we actually don't. So one example is, what about the relationship between H3O+ and OH-? If we think of our acid up here being H3O+, if we lose one proton, we saw that its conjugate base is water. If water loses another proton, we get OH-. So the difference between these two species here is 2 protons instead of 1 proton. So these two, hydronium and hydroxide, are not a conjugate acid-base pair because they differ by 2 protons instead of 1. And then the last example we'll look at is, we said that fluoride is a conjugate base of HF. So what about the relationship between sodium fluoride and fluoride? And so these two are also not a conjugate base pair because if we take our fluoride ion and it accepts a proton, we don't get sodium fluoride. They are related by a sodium ion. So by definition, that these two are not a conjugate acid-base pair. So in this video, we learned that a conjugate acid-base pair is when you have two species and they have the same formula, except one has an extra proton. So the acid has an extra proton, which it can lose to form the base.